You've seen the images after a big earthquake, right? Total devastation. But then, right in the middle of it all, there's a building still standing, almost like nothing happened. So, how in the world do they do that? How do engineers teach a massive skyscraper to literally dance with the forces of the earth and come out on top? I mean, that's the question, isn't it? The one at the heart of all earthquake engineering. Is it just pure luck? Or maybe stronger materials, better construction crews? Well, it's kind of all of those things, but it's all guided by something way more important, something fundamental. Believe it or not, the biggest difference between that pile of rubble and a building that saves lives is a rulebook. Seriously, it's a set of engineering recipes called seismic codes, and these codes, they're basically everything we've learned from every major earthquake, all boiled down into a guide that tells engineers exactly how to build for the big one. So, today we're going to crack open that rulebook. We'll talk about what it is, then we'll break down the anatomy of a building and figure out what this earthquake shove is all about. We'll even look at how engineers analyze it, dig into some details that might surprise you, and finally, get to the heart of what it means to design for something you can't even see. All right, so what exactly is this rulebook? Well, it's not just a friendly list of suggestions. No, it's a super rigorous set of standards that's all based on hard science. We're talking physics, geology, and just mountains of data from every single major earthquake we've ever been able to study. It's all about trying to predict the unpredictable. So yeah, the seismic code, it's really the foundation for everything we're talking about. And it's not some dusty old book. It's constantly being updated. It basically tells an engineer, okay, look, based on where you're building, what people are going to use it for, and the materials you've got, here's the absolute minimum strength it needs to have to survive the kind of shaking it's probably going to see. Okay, to really get how these rules work, we need a test subject, right? So let's use a great case study that's based on the examples in the Indian Seismic Code. We're going to look at a pretty standard 4-story office building, but here's the catch. It's in a super high-risk earthquake zone. Now, before an engineer can even think about the earthquake's power, they have to know one thing: the building's mass. You remember good old Newton, right? Force equals mass times acceleration. It's simple. The heavier the building, the more force the earthquake can throw at it. So step one is always the same. We gotta weigh the building. And here's where it gets really interesting. Engineers don't just weigh the concrete and steel. No way. They calculate something called seismic weight. And that includes the building itself, sure, but also a chunk of the weight of everything inside it. We're talking desks, computers, file cabinets, even the people. For our building, that all adds up to a massive 15,600 kilonewtons. To put that in perspective, that's like an earthquake having to shove around 300 elephants. Okay, so every building has two super important points. You've got the center of mass, that's its natural balance point. Then you have the center of stiffness. That's where the structure is strongest, where it can push back. So think of it this way. The earthquake shoves the center of mass, and the building's structure resists from its center of stiffness. Now, if those 2 points aren't perfectly aligned, the whole building starts to twist. And that twisting force, called torsion, is one of the most destructive things that can happen to a structure. All right, so we've weighed our building, we know its mass. Now for the big question. How do you figure out the force of the earthquake itself? Well, engineers have a term for this. They calculate something called base shear. And that's basically the total horizontal shove that the earthquake is going to hit the building's foundation with. And you guessed it, the code gives engineers a recipe for this too. It's like a checklist. First up, location. Are you in a high-risk zone, like Shillong? Okay, that's a higher force factor. Next, what's under the building? Soft soil will shake things up way more than solid rock. Then, what's the building for? A hospital is way more critical than an office, so it gets a higher importance factor. And finally, how is it built? A flexible frame that's designed to sway is treated differently than a super rigid one. So you take all those factors, you plug them into the formulas from the code, and out pops a number. For our building, that number is 1,404 kilonewtons. And what does that even mean? Well, picture this. It's like the building getting slammed sideways by the force of 10 city buses all at once. Suddenly, it's not just an abstract problem anymore. It's a real, tangible target for the engineers to design against. But here's the thing. Knowing that total shove is a huge first step, but it's not the whole story. Not even close. The real question is how does that force spread out as it goes up the building? Where are the weak spots going to be? To figure that out, engineers use two main kinds of analysis. On one hand, you've got static analysis, which we can just call the push. It's a simpler method, kind of a shortcut, that just applies that calculated force to the building. On the other hand, you've got the more complex and much more accurate method, dynamic analysis. Let's call that the shake. This is the whole shebang, a full-on computer simulation that models how the building will actually vibrate and bend and wobble during a real earthquake. And this is where it gets crazy. Look at the difference it makes. According to the data for our building, the simple push analysis suggests most of the force hits the top of the building. But the more realistic shake analysis, it tells a completely different story. Just look at the first floor. The shake shows almost 3 times more force concentrated right there at the bottom. This is an absolutely crucial difference. Getting this right can prevent one of the most dangerous types of failure, the soft story collapse. So we've covered how engineers figure out the main forces. But what's truly fascinating, to me at least, is that the real secret to a safe building is often hidden in the details, the little things you'd never think about, but that can completely change how a building acts when the shaking starts. Okay, for example, there's this concept called effective inertia. The best way to think about it is with spaghetti. A perfect computer model might see a concrete beam as being like a piece of dry, uncooked spaghetti, super rigid. But the code is smarter than that. It knows that in the real world, under stress, that concrete is going to get tiny little cracks. It becomes more flexible, more like cooked spaghetti. And engineers have to account for that real-world flexibility, not the perfect on-paper version. Or how about this? The regular brick walls between the concrete columns in an office building. You'd think they're just there to separate one room from another, right? Wrong. These infill walls actually add a ton of stiffness to the whole building. If you ignore them in your calculations, you get a completely wrong idea of how the building is actually going to shake. And the data really drives this home. Check it out. A model of our building with just its bare concrete frame has a natural wobble, or what engineers call a period, of about 1.27 seconds. But look what happens when you add those brick infill walls to the model. The period drops to just 0.56 seconds. That means the building becomes way stiffer and wobbles more than twice as fast. And that completely changes the kind of forces it's going to attract from the earthquake. And you know, the challenges don't even stop at the building itself. Engineers have to look at the ground under it. Because in certain types of soil, intense shaking can cause something terrifying called liquefaction. That's where the ground literally, temporarily turns into something like quicksand. And it doesn't matter how perfectly you design the building if its foundation suddenly sinks into the earth. So, when you put it all together, you realize that seismic design is this incredible, complex puzzle. It's a dance between dozens of things that are all connected. The dirt under the foundation, the tiny cracks in the concrete, even the brick walls between the offices. And it's a puzzle where the stakes couldn't possibly be higher. So what are the big takeaways here? If you're going to remember anything, remember this. It boils down to a few key things. How heavy is the building? Where is it located? How stiff is it? And how good is the analysis used to predict its behavior? You get those 4 things right, and you're on your way to designing a structure that can stand up to the most powerful forces on the planet. And what's the ultimate goal of all this? You might be surprised to hear it's not to make buildings earthquake-proof. Honestly, that would be practically impossible and incredibly expensive. The real goal is something called life safety. The whole point of the code is to make sure that even in a massive earthquake, the building does not collapse. It might be a total wreck afterwards, it might have to be demolished, but it will stay standing long enough for every single person to get out safely. It's designed to bend, but not break. You know, every seismic code in the world is a living, breathing document. It gets updated with the painful lessons we learn from every new disaster. They really do represent the best of what we know right now. But that leaves us with a pretty heavy question, doesn't it? As our cities get bigger and taller, and as we face all kinds of new challenges, are the rule books we're writing today really going to be enough to protect the world of tomorrow?